Okay, and as usual, we'll, after each speaker's talk, we will give some time for questions, and you can just raise your hand and we will call on you. You can unmute yourself and ask your question, or as I said, you can write a question in the chat and we will read it for you. So, and also both speakers have time left for one-on-one meetings in their schedule, so feel free, if you're interested in talking to them one-on-one, sign up for those for the rest of the afternoon. That would be great. And okay, today we're going to start with Giacomo Beccari from ESO. He got his PhD at the University of Bologna. Since then, he's been a research fellow at ESA and ESO, a support astronomer at the VLT, and a staff astronomer at ESO supporting X-Shooter and OmegaCam. And since 2019, he's been deputy head of the ESO Office for Science in Garching. He's an observational astronomer interested in the formation and evolution of stars and star clusters. And today he'll be telling us about the Gaia revolution. So Giacomo, go ahead, take it away.
Yes, thank you very much. So I'm sharing my screen. I'm pretty sure. Yeah. Okay. So, thank you very much. First of all, I would like to congratulate and thanks the organizing committee, because I've been told back in the days that basically you prioritized in the scheduling early career astronomer, and I think this is really appreciated. I as a person and also ESO, we also really want to do the same. We are trying to do the same. We gave priority to early career scientists because of as a platform for visibility. So it was I really appreciate that happening, and it was very inspiring for me as well. So I just wanted to open with this by congratulating and thanking you all. So yes, the formation of cluster in the Gaia revolution. So in this, basically, Gaia, since the time when the data were released, already with the release 1, but then with the second release and the third release, it really shows that is bringing a revolution in terms of observation and capability to distinguish and to learn about the clusters, star clusters. I'm talking about star clusters, and this is true at almost any stage of the formation and evolution. The early stage, as you can see here, at early stage when stars are just forming, and then you can move to what we call open clusters. So at the mid age, when the clusters survive, basically when they are born, they survive and they evolve as clusters, as a young cluster, and then later with globular clusters. So in all these fields, Gaia is providing unavailable level of information and discoveries. It's becoming the Gaia catalog is in a sense a discovery machine, if you want. And so let me start with the early stages of formation of stars, so stars forming clusters. This is a beautiful picture of a Tramper 14, which is a cluster in Carina. And at this age, so I'm talking about ages at the early stages. So these clusters are unique astrophysical laboratories for a huge number of topics. And I tried here to just put in bullets 4, which are, I think, the very relevant topics, which are, stars are embedded in gas, and so gas and in dust and in molecular clouds. So they form there, and we need to know we can learn about gas chemistry and gas dynamics, about distant planets, because many of these stars that form in the early stage of their formation, they are surrounded by circumstellar disk where the planet forms. So so basically it is true nowadays, it's more and more evident that we cannot study the evolution of disks without taking care of or understanding that there is an environment around them, there is a star that is evolving, so that's why still a revolution, and the mass accretion, so the way the stars or the object that is moving from the zero arrangement sequence towards the main sequence. And plus, as I said, there is an environment, there are massive stars that are photoevaporating the disks, so all these physics beyond inside the evolution of massive stars, plus the stars are evolving in a dynamical system, there are encounters, there are collisions, and this is also, all of this needs to be taken into account when studying early stages of formation of clusters. Now, we know a lot about these clusters, about the early stages of formation of stars, and what we have learned recently with this beautiful data, Álvaro Ajar is, understanding. I mean, I think is one of the leader in this sense, in this study of how star forms. And through these ALMA observations or VLA observation, you can see that you can start to see that really stars form along filamentary structures. So you have these huge filamentary structures, and stars form along these filaments. And where the filaments cross together, you form hub, and this hub you have the formation of massive stars and very likely formation of clusters. So this is all now coming out, and on the other side, if you use Gaia, and that's where Gaia comes in, by using Gaia and by using these beautiful machine learning techniques, you can explore, and using the very accurate, extraordinary accuracy of the astrometry and and the 6D space basically that Gaia offers, you can start. We are able now, and this is a very recent work. Sorry, let me move this from McBride et al. 2020, where you can see they basically studied in the old Gaia catalog, you study the premium sequence stars, and you can see these beautiful structures appearing basically everywhere. And there are several studies in the literature. The literature is huge about this, and so what Gaia is doing is really giving us the chance to disentangle structures that were in the early stages that were previously difficult to observe because of the contamination from background foreground stars. So now we can really see and detect the stars in very high details. Now, let me now jump into one result that I think is still very interesting to mention. It is about the Orion molecular cloud and Orion molecular cluster. So we know the Orion molecular cluster, just to give you a sense, this is the trapezium and this is the Orion molecular cluster. It's a well-known cluster which has been very, very much studied and is considered as benchmark of basically to study the evolution, the formation evolution of stars. And it has been one of the important points is whether there is a significant, or to which degree there is an age spread among the stars in Orion. So Orion, as I said, we know there are a lot of young stars. There are proplets. We do see few massive stars in the center in trapezium. And there were hints of the presence of an age spread among the stars. So we know let's say the median age is around 2.5, 3 million years, but there was, for example, you can see in this histogram from Reggiani, you can see that there is a hint basically of spread of age in the stars of the cluster. So this is not really monolithic. Basically, is one monolithic formation in one shot with 2.5 million years ago with a small spread, likely spread of age. Now, what we did, so we used Omega Cam, which is wide field imager at the telescope in Paraná, to perform an homogeneous study in multi-band, in optical bands, plus, so in optical RI H alpha, so RI plus narrowband H alpha image, to study the stars in Orion. And here you can see, basically, just to give you a sense, this is an image of Spitzer in the background. Here is the center of the trapezium, just to give you a dimension. So this is the Orion Nebula cluster. More or less, the size of that image is more or less this size. So just to give you a sense of the wide field that we are observing. So this is done through an imager, okay, through Omega Cam. So what we did is to basically you do the color minus diagram of the entire region that you can see here on the left and on the right. So this is as I said, color versus magnitude, and you can see this is basically this is background, foreground stars and background stars. While here you see Orion, and what we found, if you plot two isochrons, this can help you to guide your eye. Basically, you can see the presence of two apparent parallel sequences. And in fact, what we did, if you basically take this isochron, this 3 million years isochron as a reference line in the color-minus diagram, and basically then you rectify the color-minus diagram and then you estimate the distance in color of each star from the rectified sequence. What we found is the presence of three peaks. You see, so there is a peak at 3 million years plus 2 small peaks. Now, to give you a sense, just to go back here, you can imagine here you are doing the same, but what you see here is not the 3 peaks, but you see 1 peak with a continuum spread, basically. While what we found is a completely different scenario. We see the presence of 3 peaks, and in fact, if you put this in age, where the age for us are picked by spectroscopic study done by Dario, a collaborator using Apogee, basically you can see that there is what we call 3 population at 3 different ages. That's so not a single bust with an age spread, but 3 single busts, very short, one at more or less 3 million years, 1.5 million years, and 0.5 million years. So a completely different star formation events with respect to what it was thought. And with Gaia, of course, as soon as Gaia came out, we could follow up this observation, and you can see here the beauty of the use of Gaia. With Gaia, you basically can clean out the contamination from foreground and background stars, and then basically we basically could still reproduce by filtering out, even filtering out stars. And remember, when we filter out based on accuracy, photometric accuracy of the proper motion, the parallaxes, and also other filtering approaches that were suggested in several of the Gaia papers. So we did all of that, and even by filtering out stars, we still see the presence of the peaks as we were that were detected without this, distinguished, without this filtering. And that's another thing that I did very recently, just for the fun of it. So this is basically, again, the Omega account, but what I did, I cross-matched our optical catalog with the catalog of infrared, basically based on Spitzer detections published by Megiat in 2012, where these sources are also classified based on the Spitzer colors, and some of them are classified as disks, so they are identified as disks. And so what we did, we cross-match with our optical catalogs, and just to see whether, doing again the same exercise, so you rectify and then you see the distribution in color of the stars, you can still see the presence of at least 2 peaks. Then there is a tail of stars in the reddest part. Is the presence of another peak starts to be difficult to detect, but this is, I think, number statistics, so the statistics is very low. So the overall message here is that there is basically the formation of the stars in Orion seems to be not as we thought as a single burst of star formation, but more like a 3 bursts of formation separated by a few minutes, but very rapid in time. How does this can happen? And then this is the simple model that was proposed by Kroupa, Jerabkova, and collaborator. This is the picture of Teresa, which was a student at the time, and now she's a fellow at the European Space Agency. And basically, the scenario is the following. Basically, if you can imagine you have the gigantic molecular clouds, but then you start to form stars at the center. You have the first hint of star formation, and then what happened because of two-body interaction, basically the massive stars are kicked out, and this allows to establish the inflow of gas, so the formation of second generation stars. Then again, two-body starts to play a role, and through two-body, basically you have again the ejection of the massive star, and then you have the re-established ignition of gas into the center and the formation of the third generation. So that this basically the formation of the 3 generation is due to this interplay between dynamics and the formation of massive stars, and then internal dynamics that kick them out and allows basically to reestablish the formation of gas, the inflow of gas, and so the formation of the second and then the third generation of stars. So this is a very, of course, it's just an idea in a sense. We need certainly precise kinematic, and what I mean with that, we also need the radio velocities, because we need to disentangle the 3D basically information in order to be sure about the distribution, the real kinematic of the stars. But this is really something very I think very exciting, still very open question in a sense. So So in this sense, so if I can now summarize, so in a sense, what I've been trying to say with this first part is that, okay, on one side, when we think about the very early stages of formation of stars, we do clusters, we do have a lot of knowledge about, and also Gaia allow us to have a very deep new set of information about the early stages and these events. On the other side, we also know a lot about the later stages, but the big question would be what happened in between. So what happens, you can imagine you have formation of stars, you have the molecular clouds, you form the stars, the first 10 million years, and then at some point, what you can expect, these stars will form a cluster if they survive, if they are bounded enough to survive the formation, or they dissolve into the field. But what do we know about this intermediate part? So as I said, we observe this stage, but what we know about the middle stage, and that's where Gaia is. Okay, I think I saw 5 minutes, right? In fact, I'm almost done. So, and that's where Gaia is making the second, I think, a big revolution again. So if you think about the stellar system at this age, which is leaving the molecular class, which are these characteristics? And I tried to summarize here what they might be the characteristics. So they mostly dust free, detectable, is possible to be detected in the optical. They are extended, coeval, co-distant, co-moving. So all of this makes clearly the perfect target for Gaia. And this is what is happening now. So this is a seminar, a very beautiful work done by Cantat Godin, where you can see in the Gamma Velorum region, basically they discover this basically constellation of clusters and filaments in this region in sky. Sorry, I'm losing the mouse. Okay, in this region in sky, just to show, they stopped at 245 in degree in latitude. What we did the same. We looked at the same region, but we went much further. You see, instead of stopping here at 245, we went down to a much larger, a shorter, say, latitude, because we saw the presence of a cluster that was unclassified, and so we were curious about that. And that what we did, we took a catalog of the entire region, and then we used dbScan, which is a clustering algorithm, to try to see in 6 space how does this region looks like and whether there are clusters there. And what we found is the following, which is unbelievable. That's again a very beautiful result. Again, if you go back, so this was the region started before. Now we are expanding this region to a much larger area, and what we see is that this cluster here is basically connected to a filament of stars towards to the extent on the other side. And if you look at the column-magnitude diagram of this filamentary structure, is impressively coeval. So basically, it seems like the relict, a filamentary relic of stars that are left, basically the star forming area, if you want, the star forming clouds, and are now appears as with a series of clumping, which are basically the small clusters. Let's call it cluster, but I'm not sure they are really clustered. They are most likely associations. Some of them are clustered, but they are connected over an area of 260 parsecs. So this is a huge area. And just to give you a sense of what Gaia DR3 is doing now, and I'm basically finished. So you can see this is a column-magnitude diagram of the Tramper 10 cluster, okay, just as a reference. And then there are other globular clusters. Other column-magnitude diagrams that were done with stars selected using dbScan. So these stars have been selected as clustered in proper motions and in distance. So we know they are the same distance, the stars in this cluster, and they have the same proper motion. So you have these 5 subclusters, let's call it. And the beauty of it, if you look at them in space, this is where they are. So you see, again, just to give you a sense of what's happening. So you have associations at 260 parsec wide area, so far from each other, one away from each other, and they are still so impressively coeval. Okay, this is all to be understood and to be studied in more details. And this is just the youngest there is still in this region, there is also a youngest component, which is this one, which is of the order of 15 million years. And again, is quite big and overlap with the oldest one. So it's everything you see, you can see here the hint a bit also in this diagram. And then just to give a sense, so what happened in between the two stages, but I think Gaia is giving us some starts to give us some answers. So basically, it's very tempting to see a correlation between what you get at the early stages and what you're left after with these filamentary structures of star formation. How it is feasible to have a structure on such long physical scale, I don't really know. There are some simulation now coming out, but this is at least what we see, and that's why I say Gaia is making a revolution in this field. And finally, that I cannot talk about this, but just to mention that there are now also Teresa, and we are starting with through the work of Teresa, we are also starting to see the stellar streams that are different physical structures. They are not filaments, these are stellar streams. And so in fact, you can find them in clusters that are old enough to have been through basically feeling the effect of the galactic potential. And we are starting to see them very beautifully as well. But we can go to see this recent paper to see more about that. And with this, I conclude by saying that yes, Gaia is really opening opening a lot of, giving a lot of answers, but also opening new beautiful questions, I think. And the upcoming facilities that we are waiting for, they are going to help to compensate a bit the need, for example, of radio velocities in order to close the loop on these 6D basically structures that we see in sky. And with this, I thank you all for your attention.
Great, thank you very much, Giacomo. Let's everyone give a round of applause in the reactions menu. I see we already have some questions, so go ahead, Anthony.
So these long structures, don't you think that perhaps they're just the residual in Gaia of star formation in a spiral arm?
Yes, there are these. Yes, yeah, I agree. I think they are actually. I completely agree with you. Yes, we need to see properly their distribution in 3D space in the galaxy, and then be able to basically reconnect them with larger structures. And this is already happening. We can, because this study is done really in a sense on a small area, but there are many works by Kinkel and by João Alves and collaborators. They are really connecting huge star forming regions, and they do yes, follow spiral arms waves. I think yes, it's very absolutely yes. And this, we see this in other galaxies in a sense.
Mm-hmm.
Yeah, absolutely yes.
Okay, Anna, go ahead.
Hi, Giacomo, this is really nice. I have a question about the first part of the talk, specifically about the picture of kind of O-stars kind of leaving their birthplace and then kind of making room for the next kind of burst of star formation. So I was wondering, is the data on kinematics of O-stars kind of precise enough to test this picture? Can you actually see them like moving away from the
yes
clusters?
So indeed, yeah, very good question. So there are already confirmed runaway stars around the trapezium, runaway stars that are all stars that are basically that you can retroactively basically put at the center into so they are consistent with being formed into the trapezium. Then we do need as I said, very precise radio velocities in order to have a proper studies of the kinematics. And in particular, there is a bit of the big problem. I mean, the issue is that the most important part is the central region, where because there is where most of the third generation, if there is a third generation, okay, the third generation stars were born, but there is also where the density is higher, and where the Gaia data, for example, they suffer a lot because of the cluster of the stellar densities. They suffer in the sense that the proper motions are less accurate, and so it's a bit of so we lack a bit of signal in that area, and that's where we are starting to, also with Teresa, we are now looking to Gaia 3, and it's really we are struggling to find new signals, basically, or better signals yet. Maybe with the future release of Gaia, and as I said, with these facilities, we can see this more accurately. Yeah.
Great, thanks.
Yeah, thank you.
And we have one last question in the chat from Nancy Evans.
This is Charlie Ladd. I haven't been able to find my raised hand, but after you're done, I'd like to ask one question too.
Okay, I think we may be out of time, but Nancy's question is, how do you take binary stars into account?
Exactly. So the binary stars are taken into account in Gaia by using, there are, we describe this in paper, there are basically some filtering using some Gaia parameters that are released with the Gaia catalog. You can use them to filter out at least I mean, let's say not exactly binaries, but at least stars where the proper motions, or at least the proper motion and the parallactic measurement can be affected by the presence of a binary system. So the small, changes in centroid that is triggered by the presence of binary, these all can be taken into account by some filtering, by filtering them out. And this was what we did in the second paper when we used the Gaia 2. So that's what we could do so far. But of course, we cannot exclude, but there is something we need to take into consider, that the binaries, there are unresolved binaries, they would populate the second, and let's call it the second and third populations. But there, what we do see that these stars, I didn't mention this here, but these stars, they are also distributed in the sky differently with respect to the first populations. And in particular, and also they rotate. The rotation speed is different. So basically, what we do see that by aging the stars, they start to slow down in the rotation, which is expected because of the so-called disk locking. So what I'm saying with this is that if they are binaries, then you would explain why they are distributed in sky so differently with respect to the main population, and also why do they have you have a gap in between. So it means that they are basically the distribution of the mass fractions of the binary has to be very, very skewed and peaked towards equal mass binaries in a way that is this is discussed in the paper, in a way that is really, really peculiar. So I think binaries, somehow can be not completely ruled out, but they are difficult to explain. Yeah.
Very interesting. Let's everyone thank Giacomo one more time.
I want to thank you again, you all. Thank you for for attending the seminar.
And I'll hand it over to Jason.
All right, thank you. It is my pleasure to introduce our second speaker, Christina Hedges. She graduated from Cambridge in the UK in 2017. And she worked in the Kepler guest office until the end of the Kepler mission, supporting the community. Since then, she's worked mostly on exoplanet discovery and characterization with Kepler, TESS, and Hubble. She's probably best known for being a developer on Light Curve and other astronomical software that many of us here have used. And since the mission's closed out, she's now been funding herself through Rose's grants, and she is a researcher at NASA Ames. And today she's going to talk to us about an interesting technique, how to get color photometry from a black and white telescope. So let's welcome Christina Hedges.
Thanks, Jason. Hi, everybody. Thank you so much for having me. Today, I am going to tell you about a cool new technique, which I'm dubbing how to get color photometry from a black and white telescope. And so I'm going to tell you a little bit about how me and my team have increased a little bit of the information that we can get from the Kepler telescope in a really fun way. Oh, there we go. So for those of you who are not familiar, and I think probably most people here will be very familiar, the Kepler telescope was a fantastic telescope, space telescope. It had 10 years of data collection. We observed thousands of exoplanets. We confirmed thousands of exoplanets. We looked at hundreds of thousands of stars. In the second phase of the mission, we looked at stars across the ecliptic plane, and it was a really successful mission. The Kepler mission has definitely revolutionized different fields across astronomy, including exoplanets, studies of stars, studies of supernovae, even microlensing, all sorts of different kinds of fields of astrophysics. Now, Kepler is a photometric telescope. It's for getting time series, very precise time series of lots of different kinds of stars. But Kepler is a monochromatic telescope. And so what that means is Kepler has a band pass, and it's a very broad band pass, which sums all of the light through the telescope. So when we start with an image like the one on the screen, where we have this beautiful, colorful image of the universe, what the image that Kepler sees is that it has to go through this band pass, and it ends up as a sort of black and white image. What's happening here is all of the light is being summed up. And that means that we get really good precision, but it means that we lose all of this beautiful color information. Now, the Kepler telescope is made up of lots of different optical components. It has an optical path that goes through a lot of glass. It goes through a mirror, and it has to be recorded on a detector. And now each of these components, even though we would like them in an ideal universe to be completely perfect, each of them has a little imperfection. And what this can mean is that light of a different wavelength, when it goes through this optical system, actually has a slightly different path, depending on the wavelength of light. What happens to light when it comes through this optical system? Well, so first off, it bounces around through the lenses and mirrors of the telescope, and it creates the point spread function, or PSF. There's an image of the point spread function of Kepler on the left-hand side. Now, first off, you can see that it's not completely a point. It's actually got some shape to it. It has some wings. It's fairly smooth at this stage, and it's fairly detailed. You can see that this is at a resolution much greater than a pixel. What happens then is that this point spread function has to be recorded on a detector. And what that detector is doing is convolving that PSF with the response of each pixel and making a downsampled version. And so we have the point spread function, and we have the pixel response function, and these are called PSF and PRF. One of the imperfections in optical systems is that you can end up with something called chromatic aberration. In the system that's on the screen, what's happening is that you have red and blue and green light coming through the lens. And even though they come in and they are all completely overlapped, by the time they've gone through the optical system, you can see that actually the blue and red light have been spread out on the plane. What this means is that in any optical system, you can't absolutely get the red and the blue light to completely overlap without some intervention. So this chromatic aberration is something that we do know exists for Kepler. These are optical designs from Ball Aerospace, who designed lots of the telescope components. This is the PSF, that point spread function, in a blue wavelength, a green wavelength, and a red wavelength. You can see that qualitatively, these are very different. They're changing shape, there's a rotation, and the wings look quite different. Now, in reality, any source that comes through the detector is going to be not blue, green, or red, but some combination of many colors. And this effect is actually quite tiny. I'm showing it in high relief here, but this effect is very, very small. But based on the designs of the telescope, we know that we're expecting some chromatic aberration, and it will change the shape of the PSF. So the question is, the PSF should have some color dependence in it. Can we see this color dependence when we measure it with the detector? Can we look at what the detector measures and ask, does the shape change? Is there a different shape for different colors? So a lot of my background is with developing software, working directly with the telescope data, and helping other people use the Kepler data. And in particular, try to detrend and get rid of any of the telescope systematics. And so I have a lot of background in developing tools and models to do this sort of thing. And so this was what I embarked on. Could I prove that the color variability in Kepler translated to something we could measure? So to start off on this quest, we're going to need a set of objects with a known and predictable color change. And so we decided, okay, we're going to start with eclipsing binaries. Eclipsing binaries are a great test for this. If we know the temperatures of both stars, which we can get from ground-based spectra, then we have a very predictable color change and something that's very simple to model. There's an example on the screen here. We have a red star and a blue star. Whenever the blue star goes in front of the red star, the spectrum of the combined system is going to become more blue. And whenever the blue star goes behind the red star, the combined spectrum is going to become more red in a way that's very predictable if we know the temperatures of both components. And so this is the perfect sort of system for us to try and figure out, is there color information in Kepler, because we can understand it really well. So here's the plan. We're going to start out with a list of 30 bright eclipsing binaries where we know the temperatures from literature from ground-based spectra. We're going to use these detrending techniques that have been pioneered in Kepler and K2 to try and build a data-driven pixel level model so that we can account for instrumental effects and astrophysical effects at the same time. Then we're going to look at the difference between our very good data-driven model and the real data. And we're going to try and search for any correlations with the temperatures of eclipsing binaries. We're going to try and see if our model is wrong in ways that might indicate the PSF shape is changing due to color variability in eclipsing binaries. So to start out, we're going to need this pixel level model, and it's got to be really good. On the screen, I'm showing data on the left. This is real Kepler data. And on the right, I've got a pixel level model that I generated based on techniques that have been pioneered in the sort of K2 detrending era. In the middle, you can see these white pixels. Those are saturated pixels. In this work, we have to trash saturated pixels because they break a lot of our assumptions. We have picked really bright targets, so we get a really broad PSF and we get lots of pixels to do our measurements with, but we have to trash these saturated pixels. So the model that I've built here is very good, and I'll show just one pixel now on the screen. The top light curve here is the black one is an eclipsing binary in Kepler, and it's 1 pixel's worth of data from Kepler. And then the blue is my data-driven pixel model for that light curve. And then we've got residuals at the bottom, and we can see that the residuals are really good. They're sort of 100 to 200 part per million residuals, so that's great. The long swoop in the data set is an instrumental effect. That's because there's a velocity aberration and the source is very slowly moving over the detector. And then the periodic dips, that's the astrophysics, that's the eclipsing binary, and those are the eclipses that come really periodically. So we're doing a really good job at modeling this pixel, and we just apply this model to all of the pixels in order to build up this blue curve for every single pixel in the data set. Okay, so on the screen now, I'm showing that. I'm showing a summed light curve of every pixel in the observation, which is the black light curve here. That's simple aperture photometry, all the pixels in the observation. And then I've folded it at the period of the eclipsing binary. In blue, I've got the same thing, but it's our model. So I've modeled every single pixel, and this is the sum of that model, and folded at the period of the eclipsing binary. And you can see that it's that beautiful eclipsing binary phase curve that we know and love. Now what we can do is we can look at how well does this model fit. And so I'm going to show you the reduced chi-squared of the model fit for the whole image stack as a function of phase. So this is, reduced chi-squared, goodness of fit. On the bottom now, you can see this goodness of fit as a function of phase. It's very correlated with the phase of the eclipsing binary. You can see, for example, there is a significant deviation during secondary eclipse. The model fits much more poorly during secondary eclipse than it does out of secondary eclipse. You can also see during primary eclipse, there is this W shape. So it's fitting very poorly during ingress and egress during the primary. Okay, so this is very strong evidence that what we're seeing is that the model fits poorly during times where there's a significant color change in the eclipsing binary. Our model does not have built into it the ability to change shape. And when we investigate this deeper, this change in reduced chi-squared, a significant reduced chi-squared, is equivalent to saying the PSF shape changed significantly and deviated from our model during those times. Let's try a case where we know that there shouldn't be any color variability. So this is the same plot as before, but now we're looking at an exoplanet. This is Kepler 1b, Exoplanets don't really emit any light in the bandpass of Kepler. And so when they transit, we know that this should be gray. There should be no color information in this system, as far as Kepler is concerned. So on the top, we have the simple aperture photometry in black. Blue is our model, which is summed up over all pixels. And then we have the reduced chi-squared. How well does the model fit? You can see the model fits really well at all times. There's no bump during transit where it fits significantly more poorly. This shows that there isn't any significant shape change to the PSF at any point during the light curve. And this is exactly what we would expect if we would attribute this shape change to color. So in the paper that I put out recently, we go into a great deal of detail in proving that this shape change really is a change in color. I'll show you a little bit of that here, but there's a lot more detail in the paper. So we've used our data-driven model, and now we have a model of the eclipsing binaries, which we can use just basic transiting eclipsing binary model with black bodies with the temperatures. If we do this, we can combine those two models and estimate what is the wavelength in each pixel of the observation. Okay, so now on the screen, I'm showing you an example of the true colors of each pixel in the observation of that eclipsing binary that I'd shown you. This is the colors that you would see with your human eye. You can see that the pixels in the middle are a little bit more red, and the pixels on the edge are a little bit more yellow. You can also see over here, there are black pixels. That's where we're actually dipping slightly into the infrared. What this means now is that since we've assigned wavelengths using this model of the eclipsing binaries, and by using this very bespoke detrending model, we can now select an aperture based on those wavelengths and build color photometry. Now, if we sum up pixels that are very similar in wavelength, we're going to end up with a light curve at one wavelength. And if we then pick different pixels, we can create a different wavelength color photometry time series. I'm showing you an example of this on the board. This is that same eclipsing binary. So black dashed line, that's all of the pixels summed up. You've already seen this. This was the black light curve from earlier. The red light curve is pixels that this model has shown are redder. And the blue light curve are pixels this model has shown are bluer. And what you can see is that the blue light curve has a much shallower secondary eclipse, which is exactly what you'd expect. I'll show you a little zoom in. So you can see here, this is the same light curve up here. So the primary eclipse down here, which is this part here, you can see as we zoom in, the sides of the primary eclipse, they have this very gentle bowing to them. You can see the red light curve is very gently bowed inwards. This is because there's a change in limb darkening at different wavelengths. And so that's further evidence that we are truly seeing different wavelengths, because we can see the limb darkening law changing. You can see the secondary eclipse, which is this part here and here. When you zoom in on that, you see this really beautiful gradient between the different light curves at different wavelengths. The secondary eclipse is much shallower in a blue light. You can also, it's a little bit hard to see by eye, but the limb darkening law is also changing during that secondary eclipse. And then finally, we've got the phase curve, which is the sort of slopey shoulders you can see here. You can see that that phase curve is changing greatly during at each different wavelength. You see that at different wavelengths, we're seeing into different depths of the atmosphere of the eclipsing binary, and so we're seeing a slightly different phase curve. So this is very, very exciting, because we've been able to take a black and white telescope and we've been able to pull out real color photometry out of it, and we can show that it really is color. We can separate them into different wavelengths of light, create different wavelength light curves, and create kind of coarse rubbish spectra out of it, which gives us really cool new information about eclipsing binaries. The model that I've set up here is limited. So the model that I set up in this first paper is excellent to show that it really is a real effect, it's measurable, and we can do something with it. But in this first work, we required eclipsing binaries, crucially, to make this calibration for the wavelength of each target and the wavelength of each pixel. We wouldn't have that across the entire focal plane. To make a real calibrated color model of what the Kepler telescope sees will take a lot more effort. It would be a lot of work to try and calibrate this for every single target in the Kepler detector. But even if we are just limited to bright targets, we now know that a PRF shape change indicates that the target changed color. And this is a great deal of information that we can now use to benefit us. So what is this good for? If we have just the things that I've told you today, what is it good for? Here's a great example of one of the things that it's useful for. At the top, we have a true planet. I think this is again Kepler-1. On the color bar, I'm showing the reduced chi-squared, which is how well does this model fit. Remember, the model cannot change shape. And so any change in the reduced chi-squared indicates that there was a significant shape change during those times or during that phase. The true planet on the top has no significant reduced chi-squared at any point. The false positive on the bottom, which I chose to be roughly equivalent depth, roughly equivalent duration, and roughly equivalent magnitude, does show a very significant color change. It shows a very significant reduced chi-squared, indicating a shape change, indicating that it changed color. And what this means is it's a false positive. It's a grazing eclipsing binary, and that's why it changed color significantly. So this technique, without any more information, can be used to help validate eclipsing binary, transiting planets and show that they are not eclipsing binaries. Great. Here's another example of something we can do. This is a pulsator that was observed during Kepler, and we have this reduced chi-squared metric again. And you can see that the color and, well, the shape and therefore color is changing very significantly during this phase. We can use this to intercompare different kinds of pulsators and learn more about pulsators and what's going on in their atmospheres. This is something that excites me. On the screen now, I'm showing a very variable active star. You can see that there's this sinusoidal pattern in the star. There are flares that go off during this observation pretty often. And you can see that during flares, the model fits significantly more poorly. This is because flares are very, very hot and very, very bright. And so they greatly change the temperature of that, or the measured spectrum of that target over a short amount of time. What would be really interesting to do would be to dig into this further and use this technique to intercompare flares within a single very active star and try and understand more about how temperatures vary from flare to flare. So I think this could be very interesting. Okay, so question on perhaps many people's minds is going to be, how do we use this further? I think one of the next things that we can do with this technique is to use this on TESS. TESS has smaller optics, it's got lenses, it's got lots of glass. TESS is going to have more chromatic aberration and less corrections than Kepler did. And what this means is that this is likely to be a more significant effect in TESS, and TESS has a lot more targets in and a lot more bright targets than Kepler. And so I'm really excited to take this technique and try and apply it to the TESS field and see if we can do the same trick of both looking for shape changes to identify false positives and also looking at the eclipsing binaries and seeing if we can pull out that color resolved time series. Okay, so to sum up, the Kepler data has a real measurable wavelength dependence that we can use to get a color photometry from a black and white telescope, which is mind-blowing. We can use this to better understand eclipsing binaries with the model that I've already presented. We can definitely do that. We can also use it to improve our understanding of flares, supernovae, pulsators, and potentially lots more using the model that we have in hand. If we improve the model by potentially doing a much more complicated model of the PRF, we could unlock even more. Please check out the publication. It's now all published. If you want to know more, we went into a lot more detail in proving that this is a real effect and proving that it is not other kinds of telescope effect like nonlinearity. And I'd be really happy to take any questions or chat with anybody offline.
Okay, fantastic. Let's all thank Christina. And if you have questions, you can raise your hand. It looks like Zoom just updated something, and some people may not have the raise hand feature. So you can just type in the chat, I have a question, or you can type your question in the chat. But feel free to raise your hand if you've got it, or type in the chat if you don't. So while we're waiting for people to find out if they have a raise hand feature, I have a question. You're known for making these tools available to the public. Is this tool coming to the public? Is it already here and I just haven't noticed? Or do you have...
Yeah, this tool is not, it is publicly available. Every piece of code that I wrote for it is on GitHub. It is not packaged as a beautiful pip installable documented technique, because that takes a lot of extra work. Certainly, I've been trying to put up tutorials about how to do the sort of cheaper, dirtier, nastier technique that works very well for flares. I've been trying to post tutorials online about how to do that.
Great. Yeah, that'll be very, very useful, because this sounds hard to put together. Great. Any other questions from the audience? There is one question. Steve, do you want to unmute yourself, or do you want me to read it?
Sure, I guess I could unmute. Hi. Great talk. This is really exciting. The question is whether there's any hope of applying this technique to Spitzer exoplanet data. There's only one object in the field of view at a time, so you'd have to base it on the optical model alone, but the optical model should be pretty good.
Right. Yeah, I think I would have to think about that a little bit more to think about how that would be useful. Certainly, you know, it's an optical system, so it's going to have some amount of this effect. It's just whether we can use that to benefit the Spitzer observations. I think I would have to think about that a little bit more.
Okay, thanks.
Yeah, it's certainly a interesting technique that I had never even considered, that could be very powerful for many telescopes. Any other questions? Got a couple more minutes if there's questions. If not, we will thank our speakers again, both of them, and we'll see you guys next week. Thanks, everybody.
Thanks for having me.
Thank you very much.